So how do we think about this in the context of a signal chain, leading to thinking about smart devices here? So the signal chain from sensor to cloud provides many opportunities to extract more valuable insights. Starting at the network edge on the left-hand side here of this slide, physical phenomena such as vibration are sensed, measured, and transformed into data. Technologies such as MEMS, analog front ends, data conversion, signal processing, ultra-low power systems, and energy harvesting, microcontrollers, and connectivity enable this with greater precision, speed, and at lower power. And Analog Devices has a long legacy of developing and deploying such technologies to solve our customers' toughest problems. Increasingly, these capabilities are being augmented by algorithms and domain knowledge to extract insights and provide interpretation at the network edge. Gateway devices provide additional opportunities for data aggregation and algorithm deployment closer to the network edge. And finally, deep data history coupled with data analytics capabilities provide the capabilities to detect and identify patterns in system behavior. Predictive and prescriptive algorithms and analytics provide the capabilities to enable decisions, the basis for taking action to improve system performance. Now, IoT technologies enable the increasing automation of this process, thereby enabling more efficiencies. And every transformation along this journey can be considered a smart step or a smart event in that it extracts more valuable information and insights. And every smart step is an opportunity to create and capture value. So let's just look at some aspects of the signal chain for a moment and maybe talk about some partitioning trade-offs. As I just mentioned, the signal chain from sensor to cloud provides many opportunities to extract more valuable insights. These insights are gained by processing signals at different stages along the way. Options include the edge node, a gateway, and the cloud in this case. And there are trade-offs associated with processing at each of these stages. Edge devices can have the advantages of small footprint, offer the ability to provide feedback directly, can be extremely low power and runoff energy harvested runoff harvested energy for extended periods of time. Edge devices can also be limited in processing power, communications capabilities, and data aggregation capabilities. There's also the question of security, especially physical security, and the challenges of managing these devices remotely during their lifetimes. At the gateway, there is more substantial processing power available, and data can be aggregated from multiple sensors and sources. There are potentially more analytics capabilities available too. They will typically run a full operating system stack, such as Windows or Linux, are more IT network friendly and more secure. However, they are typically not low power and will still be somewhat limited in their data storage and ability to aggregate data from a wide variety of sources. Physical security may still be a concern depending on how they are deployed. On the right-hand side, the cloud offers potentially very large compute and storage resources. It offers the best security and a range of different deployment and development service levels, such as infrastructure as a service, also known as IaaS, platform as a service, software as a service, to suit a variety of different needs. There are a large variety of open source and commercial development tools available, and it offers the best scalability. However, server hosting will be required. Connectivity management can be complicated to make really robust, and the services can also be expensive, especially as storage and data rate over the network starts to go up. Therefore, overall here, there are many things to consider when deciding how to partition an IoT system, and evaluating the trade-offs will be very dependent on specific use cases. So, if we look at IoT systems today, there's a tendency to be able to get the data, or to try and get the data to the cloud as quickly as possible and focus all the processing there. While this can be an important first step in deploying and developing IoT systems, it is not very optimal. There's never any wisdom and knowledge generated at the node. This approach can also be very power hungry and bandwidth intensive, because you need to convert and send all of the data to the cloud. In many cases, data communications can be the most power-hungry part of a system, so managing this is key to creating low-power optimized systems. Moving forward, we see IoT evolving to more intelligence at the node, where intelligent or smart sensing at the node turns data into information locally. Now, this can lower the overall power consumption of a system assuming that the transmission power and moving data is the largest single element. It can lower latency because you have the information right there in the node itself. It can reduce bandwidth waste. And given the proximity to the edge, this enables a move from reactive IoT to predictive and real-time IoT. Since more valuable information and insights are available directly on the node, it enables local feedback loops to be created, which can be which can be very, very powerful. These attributes are very important in a range of different IoT applications.